Introduction to ISATAP. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving deep into ISATAP, which stands for Intra-Site Automatic Tunnel Addressing Protocol. ISATAP is an IPv6 transition mechanism that was developed to solve a very specific problem during the long transition period from IPv4 to IPv6. This protocol is particularly important in enterprise environments where both IPv4 and IPv6 need to coexist seamlessly within the same network infrastructure. The fundamental challenge that ISATAP addresses is this: how do we enable IP version 6 connectivity between hosts on an IP version 4 network without requiring extensive infrastructure changes? Think about large corporate networks that were built entirely on IP version 4. These networks have routers, switches, and applications that may not support IP version 6 natively. Upgrading all of this equipment simultaneously would be prohibitively expensive and operationally disruptive. ISATAP provides an elegant solution by creating automatic tunnels that carry IP version 6 packets inside IP version 4 packets. What makes ISATAP particularly interesting is that it operates entirely within a single site or administrative domain. This is what the intra-site part of the name refers to. Unlike other transition mechanisms like 6-4 or Teredo that are designed for internet-scale connectivity, ISATAP is optimized for use within an organization's internal network. This design decision allows ISATAP to make certain assumptions about the network topology and security model that wouldn't be valid on the public internet. ISATAP was defined in RFC 5214, which was published in 2008. The protocol has been widely implemented in operating systems including Windows, Linux, and various network equipment. Microsoft Windows has had built-in ISATAP support since Windows XP Service Pack 1, and it remained enabled by default through Windows 7. Understanding ISATAP is essential for network engineers managing dual-stack environments or planning IPv6 migration strategies. The IPv4 to IPv6 transition challenge. Before we can fully appreciate how ISATAP works, we need to understand the broader context of the IPv4 to IPv6 transition problem. IPv4, which has served as the foundation of Internet communication since the 1980s, uses 32-bit addresses. This gives us a theoretical maximum of approximately 4.3 billion unique addresses. Although this seemed like an enormous number when the protocol was designed, the explosive growth of the Internet has completely exhausted the IPv4 address space. IPv6 was developed to solve this address exhaustion problem. It uses 128-bit addresses, providing an address space so large that we could theoretically assign unique addresses to every atom on the surface of the Earth and still have addresses left over. However, IPv6 is not backward compatible with IPv4. This means that IPv4-only devices cannot communicate directly with IPv6-only devices, and vice versa. The two protocols are fundamentally different at the network layer. This incompatibility creates a massive operational challenge. We cannot simply flip a switch and upgrade the entire Internet from IPv4 to IPv6 overnight. The transition must be gradual, potentially taking decades. During this transition period, networks need to support both protocols simultaneously. This dual-stack approach is workable but creates complexity in routing, addressing, and network management. Several transition mechanisms were developed to ease this migration. These include dual-stack operation where hosts run both IPv4 and IPv6 simultaneously, translation mechanisms like NAT64 that convert between the protocols, and tunneling mechanisms that encapsulate one protocol inside the other. ISATAP falls into this last category. It allows IPv6 traffic to traverse IPv4-only network infrastructure by wrapping IPv6 packets inside IPv4 packets. The receiving end then unwraps the IPv6 packet and processes it normally. ISATAP Architecture Overview. Let's examine the architecture of ISATAP in detail. At its core, ISATAP defines a method for automatically generating IPv6 addresses and creating tunnels between hosts on an IPv4 network. The architecture consists of three main components: ISATAP hosts, ISATAP routers, and the IPv4 infrastructure that connects them. An ISATAP host is any device that implements the ISATAP protocol. This could be a workstation, server, or network device. Each ISATAP host has at least one IPv4 address and uses ISATAP to obtain an IPv6 address. The IPv6 address is not manually configured. Instead, it is automatically derived from the host's IPv4 address using a specific algorithm that we'll explore in detail later. The ISATAP router serves as the gateway between the ISATAP tunnel interface and native IPv6 networks. Think of it as a bridge between the IPv4 world where ISATAP operates and the IPv6 world that the hosts want to reach. The ISATAP router must have both IPv4 connectivity to reach ISATAP hosts and IPv6 connectivity to forward traffic to IPv6 destinations. It advertises IPv6 prefixes to ISATAP hosts and routes IPv6 packets between the ISATAP interface and native IPv6 interfaces. The underlying IPv4 infrastructure is the existing network that carries the encapsulated traffic. This is the key advantage of ISATAP. It leverages the existing IPv4 network. The IPv4 routers and switches don't need to understand IPv6 at all. They simply see IPv4 packets with protocol 41, which is the protocol number for IPv6 in IPv4 encapsulation. These packets are routed normally using existing IPv4 routing tables. The communication flow works like this. When an ISATAP host wants to send IPv6 traffic, it first checks if the destination is another ISATAP host on the same network or if it needs to go through an ISATAP router. For destinations within the ISATAP domain, hosts can communicate directly using host-to-host tunnels. For destinations outside the ISATAP domain, traffic goes through the ISATAP router. The entire process is transparent to applications running on the host, which see only normal IPv6 connectivity. ISATAP address format. One of the most elegant aspects of ISATAP is how it generates IPv6 addresses. The addressing scheme is defined precisely in RFC 5214 and follows a specific structure that embeds the IPv4 address into the IPv6 address. This embedding allows hosts to automatically derive their ISATAP IPv6 address from their existing IPv4 address without any manual configuration. An ISATAP address consists of 128 bits divided into several parts. The first 64 bits form the subnet prefix, which is provided by the ISATAP router through router advertisements. This prefix identifies the IPv6 network that the ISATAP hosts belong to. The subnet prefix follows standard IPv6 format and is typically a /64, meaning the first 64 bits define the network and the remaining 64 bits identify the interface. The next 32 bits are fixed and always contain the value 0000:5EFE in hexadecimal notation. This is a reserved identifier that marks the address as an ISATAP address. When you see 5EFE in an IPv6 address, you can immediately recognize it as ISATAP. The hexadecimal value 5EFE is chosen because it is easy to recognize and unlikely to conflict with other addressing schemes. The final 32 bits contain the IPv4 address of the ISATAP host. This is the key to automatic address generation. The IPv4 address is simply converted to hexadecimal and placed in the last 32 bits of the IPv6 address. For example, if a host has IPv4 address 192.0.2.1, this converts to C0.00.02.01 in hexadecimal. or C000:0201 when formatted as part of an IPv6 address. So the complete ISATAP address might be 2001:db8:1:2:C000:0201, where 2001:db8:1:2 is the prefix, 5EFE is the ISATAP identifier, and C000:0201 is the embedded IPv4 address. ISATAP address configuration example. Let's work through a concrete example of how ISATAP addresses are configured and used. Imagine we have a corporate network with IPv4 address space 10.0.0.0/8. The network administrator wants to enable IPv6 connectivity for internal resources and has been assigned the IPv6 prefix beginning with 20 ending with 48 from their internet service provider. First, an ISATAP router is configured. This could be a dedicated router or a server running routing software. The router is assigned IPv4 address 10.1.1.1 on the internal network and has native IPv6 connectivity to the Internet. The administrator configures the ISATAP interface on this router with the prefix 2001:db8:abcd:1:/64. This prefix will be advertised to ISATAP hosts through router advertisements. Now, consider a workstation with IPv4 address 10.20.30.40. When ISATAP is enabled on this workstation, it needs to discover the ISATAP router. This discovery can happen through DNS by querying for a hostname called isatap.company.com, or the router address can be configured manually. Once the router is discovered, the workstation begins listening for router advertisements from 10.1.1.1. The ISATAP router sends periodic router advertisements containing the prefix 2001:db8:abcd:1:/64. When the workstation receives this advertisement, it automatically generates its ISATAP address. It takes the received prefix, appends the ISATAP identifier 0000:5EFE, and then converts its IPv4 address to hexadecimal. The IPv4 address 10.20.30.40 converts to 0.14.1e.28 in hexadecimal, which formats as 0A14:1E28 in IPv6 notation. The complete ISATAP address becomes 2001:db8:1:5EFE:0A14:1E28. This address is now assigned to the ISATAP tunnel interface on the workstation. The workstation can use this IPv6 address to communicate with IPv6 resources. When it sends an IPv6 packet, the ISATAP implementation encapsulates it in an IPv4 packet with the destination being the ISATAP router at 10.1.1.1. The router receives the IPv4 packet, extracts the IPv6 packet, and forwards it according to its IPv6 routing table. Packet encapsulation in ISATAP. The encapsulation mechanism is fundamental to how ISATAP operates. When an IPv6 packet needs to traverse an IPv4 network using ISATAP, it must be wrapped in an IPv4 header. This process is called Protocol 41 encapsulation because IPv6 is assigned protocol number 41 in the IPv4 protocol field. Understanding this encapsulation is crucial for troubleshooting and network security configuration. Let's examine the structure of an encapsulated packet in detail. The outer IPv4 header contains standard IPv4 fields, including source address, destination address, and protocol number. The source address is the IPv4 address of the ISATAP host sending the packet. The destination address is either another ISATAP host for host-to-host tunnels or the ISATAP router for packets destined outside the ISATAP domain. The protocol field is set to 41, indicating that the payload is an IPv6 packet. Inside this IPv4 packet sits the complete IPv6 packet, including its own IPv6 header and payload. The IPv6 header contains the source and destination IPv6 addresses, which are the ISATAP addresses we discussed earlier. The IPv6 payload could be any IPv6 traffic, TCP segments, UDP datagrams, ICMPv6 messages, or any other IPv6 protocol. From the perspective of the IPv6 layer, this is just a normal IPv6 packet traveling across a network. The total packet size is important for network design. The IPv6 packet is not modified, it is simply placed inside an IPv4 packet. This means the total packet size is the IPv6 packet size plus 20 bytes for the IPv4 header. If the resulting packet exceeds the maximum transmission unit of the IPv4 network, fragmentation may occur. Most networks use a maximum transmission unit of 1500 bytes, so the effective maximum transmission unit for IPv6 over ISATAP is typically 1480 bytes to account for the IPv4 header overhead. When the packet arrives at its destination, the decapsulation process reverses the encapsulation. The receiving ISATAP host or router strips off the outer IPv4 header and passes the inner IPv6 packet to the IPv6 processing stack. Applications using IPv6 have no awareness that their packets traveled through an IPv4 tunnel, as this process happens transparently. This transparency is one of the key benefits of the tunneling approach. Router discovery and configuration. ISATAP hosts need a mechanism to discover ISATAP routers on the network. This discovery process is essential because hosts need to know where to send IPv6 traffic destined for networks outside the local ISATAP domain. RFC 5214 defines two primary methods for router discovery: DNS-based discovery and manual configuration. The DNS-based discovery method is the more automated approach. The ISATAP specification defines a special DNS naming convention. When an ISATAP host initializes, it queries DNS for a hostname constructed by prepending ISATAP to the host's DNS suffix. For example, if a host's fully qualified domain name is workstation.engineering.company.com, it would query for isatap.engineering.company.com. The DNS server should have a record pointing this hostname to the IPv4 address of the ISATAP router. This DNS approach provides flexibility for network administrators. They can change the ISATAP router address by simply updating the DNS record, and all hosts will automatically discover the new router location when they refresh their DNS cache. However, it does require proper DNS infrastructure and introduces a dependency on DNS availability. If DNS is unavailable or misconfigured, ISATAP hosts cannot discover the router automatically. The manual configuration method involves explicitly specifying the IPv4 address of the ISATAP router in the ISATAP configuration of the host. On Windows systems, this can be done using the netsh interface ISATAP set router command, followed by the IPv4 address of the router or the host name. While this method does not rely on DNS, it is less flexible because every host must be individually configured, and any change to the router address requires reconfiguring all hosts. Once a router is discovered, the ISATAP host sends a router solicitation message. This is an ICMPv6 message encapsulated in IPv4 and sent to the router's IPv4 address. The router responds with a router advertisement containing the IPv6 prefix that hosts should use for their ISATAP addresses. These router advertisements are sent periodically, not just in response to solicitations. Hosts listen for these advertisements to maintain their configuration and detect when the router becomes unavailable. ISATAP communication patterns. ISATAP supports two fundamental communication patterns: host-to-router communication and host-to-host communication. Understanding these patterns is essential for designing ISATAP networks and troubleshooting connectivity issues. Each pattern has different encapsulation behavior and routing requirements. Host-to-router communication is the most common pattern. This occurs when an ISATAP host needs to reach an IPv6 destination that is not on the ISATAP network. The host recognizes that the destination is off-link by examining the IPv6 address prefix. If the destination prefix does not match the local ISATAP prefix received in router advertisements, the host knows it must send the packet to the ISATAP router. In this scenario, the host creates an IPv6 packet with the destination being the remote IPv6 address it wants to reach. This IPv6 packet is then encapsulated in an IPv4 packet with the destination being the IPv4 address of the ISATAP router. The ISATAP router receives the IPv4 packet, extracts the inner IPv6 packet, and forwards it according to its IPv6 routing table. This might involve sending it to another router on a native IPv6 network, or it might involve further tunneling depending on the network architecture. Host-to-host communication is an optimization for when two ISATAP hosts on the same IPv4 network want to communicate. Because ISATAP addresses embed the IPv4 address, an ISATAP host can extract the IPv4 address from the destination ISATAP IPv6 address. If the extracted IPv4 address is reachable on the local IPv4 network, the host can establish a direct tunnel to the destination host without going through the router. This host-to-host tunneling is more efficient because it eliminates the router as an intermediary. The source host encapsulates the IPv6 packet in IPv4 with the destination being the extracted IPv4 address of the target host. The target host receives the packet, decapsulates it, and processes the IPv6 content. This direct communication reduces latency and router load. However, it requires that both hosts support ISATAP and that IPv4 connectivity exists between them. Security considerations. Security is a critical consideration when deploying ISATAP. Tunneling mechanisms introduce unique security challenges that do not exist in native IPv4 or IPv6 networks. Network administrators must understand these challenges and implement appropriate controls to maintain network security. One fundamental security concern is that ISATAP creates automatic tunnels that may bypass existing IPv4 security controls. Many organizations have invested heavily in IPv4 firewalls, IDS, and network access controls. These systems are configured to inspect and filter IPv4 traffic based on source addresses, destination addresses, and ports. However, when IPv6 traffic is encapsulated inside IPv4 Protocol 41 packets, these security devices cannot see the inner IPv6 headers and payloads. This means that an attacker could potentially use ISATAP to tunnel malicious IPv6 traffic through an IPv4 firewall that doesn't inspect Protocol 41 packets. The firewall would see only IPv4 packets between internal hosts and might allow them based on source and destination addresses, not realizing that unauthorized IPv6 traffic is being carried inside. This is sometimes called the tunnel vision problem. Security devices are blind to traffic inside tunnels. Address spoofing is another concern. Because ISATAP addresses are derived from IPv4 addresses, an attacker who can spoof IPv4 addresses can also spoof ISATAP addresses. If an attacker sends packets with a forged IPv4 source address, and these packets contain ISATAP traffic, the resulting IPv6 communication will appear to come from the ISATAP address associated with that spoofed IPv4 address. This can be used to bypass IPv6 access controls or to impersonate other hosts. Rogue ISATAP routers represent a significant threat. If an attacker can configure a system to respond to ISATAP router discovery requests, they can advertise themselves as an ISATAP router. Hosts that discover this rogue router will begin sending their IP version 6 traffic to the attacker. The attacker can then intercept, modify, or drop this traffic. They could also advertise incorrect prefixes, causing hosts to generate incorrect ISATAP addresses and disrupting connectivity. ISATAP security best practices. Given the security challenges we just discussed, implementing ISATAP securely requires careful planning and multiple layers of defense. Let's explore the best practices that organizations should follow when deploying ISATAP in production environments. First and foremost, firewall rules must explicitly account for Protocol 41 traffic. Rather than blindly allowing all Protocol 41 packets, firewalls should implement specific rules that permit ISATAP traffic only between authorized hosts and routers. For example, rules might allow Protocol 41 traffic from any internal host to the designated ISATAP router's IPv4 address, but block Protocol 41 traffic between arbitrary internal hosts unless host-to-host tunneling is specifically required and controlled. Many modern firewalls have the capability to perform deep packet inspection on tunneled traffic. These devices can decapsulate Protocol 41 packets, inspect the inner IPv6 headers and payloads, and apply security policies based on the IPv6 content. This prevents the tunnel vision problem by making the firewall aware of what is actually being carried inside the tunnel. Organizations deploying ISATAP should invest in firewall platforms that support this capability. Network segmentation is another important control. The ISATAP router should be placed in a network segment that is carefully controlled and monitored. Access to this segment should be restricted to administrators, and all traffic to and from the router should be logged. If possible, the router should be a dedicated device rather than a general-purpose server that runs other services. This reduces the attack surface and makes it easier to audit the router's configuration and operation. To prevent rogue ISATAP routers, several techniques can be employed. One approach is to use DHCP options to centrally distribute the ISATAP router address to hosts, rather than relying on DNS discovery. This makes it harder for an attacker to redirect hosts to a rogue router through DNS poisoning. Additionally, DNS security extensions, or DNS-SEC, can be deployed to ensure the authenticity of DNS responses, making it much more difficult for attackers to inject false ISATAP router addresses into DNS queries. Organizations should also consider implementing IPsec to secure ISATAP traffic. IPsec provides authentication and encryption for IPv6 packets. When used with ISATAP, IPsec ensures that even if the IPv4 network is compromised, the IPv6 traffic remains confidential and authenticated. This is particularly important when ISATAP is used to carry sensitive traffic such as database connections or administrative traffic. ISATAP implementation on Windows. Windows operating systems have included built-in ISATAP support since Windows XP Service Pack 1, making it one of the most widely deployed ISATAP implementations. Understanding how to configure and manage ISATAP on Windows is essential for network administrators working in mixed IPv4 and IPv6 environments. The Windows implementation is robust and provides comprehensive command line tools for configuration and troubleshooting. The primary tool for managing ISATAP on Windows is the NETSH command line utility. NETSH, which stands for Network Shell, is a powerful scripting utility that allows configuration of various network components. For ISATAP specifically, we use the interface ISATAP context within NETSH. This context provides commands to enable or disable ISATAP, configure the router address, view current status, and troubleshoot connectivity issues. By default, on modern Windows systems, ISATAP is disabled due to security considerations. Microsoft made this change starting with Windows 7 and Windows Server 2008 R2 because ISATAP can potentially bypass network security controls if not properly managed. To enable ISATAP, an administrator must explicitly run the command netsh interface ISATAP set state enabled. This design ensures that ISATAP is only active when intentionally configured by someone with administrative privileges. Once enabled, the ISATAP interface appears as a separate network adapter in Windows. You can view it using standard Windows networking tools like ipconfig or the Network Connections Control Panel. The interface will have a name like isatap.domain.com or similar. This interface has its own IPv6 address, which is the ISATAP address we discussed earlier. The interface also participates in IPv6 routing decisions, meaning that Windows will use it to reach IPv6 destinations when appropriate. Configuration of the ISATAP router is critical. Windows can discover the router automatically via DNS, or you can set it manually. The manual approach is often preferred in enterprise environments because it provides more control and does not rely on DNS infrastructure. You can specify exactly which ISATAP router the host should use by employing the command netsh interface ISATAP set router, followed by an IP address or host name. This configuration persists across reboots and becomes part of the Windows registry settings for the network interface. ISATAP implementation on Linux. Linux systems implement ISATAP support through kernel modules and user space tools. The Linux implementation is highly flexible and can be configured for a wide variety of network scenarios. Unlike Windows where ISATAP is built into the operating system, Linux requires some manual configuration but provides more granular control over tunnel parameters and routing behavior. The core ISATAP functionality in Linux is provided by the SIT module, which stands for Simple Internet Transition. This kernel module implements IPv6 in IPv4 tunneling, including ISATAP mode. The SIT module must be loaded into the kernel before ISATAP can be used. On most modern Linux distributions, this module can be loaded automatically or on demand. You can verify if the module is loaded by examining the output of lsmod or by checking the kernel module directory. To create an ISATAP interface on Linux, you use the IP command from the iproute2 package. This command suite has largely replaced the older ifconfig and route commands in modern Linux distributions. The IP tunnel command is specifically used to create and manage tunnel interfaces. For ISATAP, you create a tunnel with mode SIT and then configure it with the ISATAP router address as the remote endpoint. One important aspect of Linux ISATAP configuration is address assignment. Unlike Windows, which automatically generates the ISATAP address based on the host's IPv4 address, Linux requires explicit address configuration. You must manually calculate the ISATAP address or use a script to derive it from the IPv4 address. This gives more control, but it requires more initial setup work. Once the address is assigned to the interface, it functions like any other IPv6 address on the system. Linux also requires explicit routing configuration for ISATAP. You need to add routes that direct IPv6 traffic to use the ISATAP tunnel interface. This typically involves adding a default IPv6 route or specific routes for certain IPv6 prefixes through the tunnel. The flexibility of Linux routing allows for sophisticated setups where different IPv6 destinations can be reached through different mechanisms, with ISATAP being just one option among many. ISATAP router configuration. Configuring an ISATAP router is more complex than configuring an ISATAP host because the router must bridge between the IP4 and IP6 worlds. The router needs both IP4 connectivity to communicate with ISATAP hosts and IP6 connectivity to forward traffic to IP6 destinations. It also must run services that advertise the ISATAP prefix to hosts and handle router solicitation messages. The first requirement for an ISATAP router is dual stack capability. It must have both IPv4 and IPv6 addresses configured on appropriate interfaces. The IPv4 address is used for communication with ISATAP hosts over the tunnel. The IPv6 address or addresses are used for native IPv6 communication with other routers and destinations. These interfaces can be physical network adapters or virtual interfaces depending on the network architecture. The ISATAP tunnel interface on the router is configured similarly to hosts, but with some key differences. The router's tunnel interface must be configured to accept connections from multiple ISATAP hosts, not just communicate with a single peer. This means the tunnel is configured in a mode that allows dynamic peer addresses. On Linux, this is accomplished using the SIT module with appropriate netfilter rules to handle multiple source addresses. Router advertisements are central to ISATAP operation. The router must send periodic IPv6 router advertisement messages to ISATAP hosts. These advertisements contain the IPv6 prefix that hosts should use for their ISATAP addresses, as well as other configuration parameters like default gateway information and DNS server addresses. The router advertisement daemon, typically RADVD on Linux systems, is configured to send these advertisements through the ISATAP tunnel interface. The RADVD configuration file must specify the ISATAP tunnel interface and the prefix to advertise. Additional parameters control how frequently advertisements are sent and what flags are set in the advertisements. For ISATAP, it is important to set appropriate prefix lifetimes so that hosts know how long their addresses remain valid. The managed and other configuration flags can be set to indicate whether hosts should use stateful address configuration like DHCPV6 in addition to the ISATAP addresses. Troubleshooting ISATAP connectivity. Troubleshooting ISATAP issues requires a systematic approach because problems can occur at multiple layers of the network stack. Issues might be related to IPv4 connectivity, tunnel configuration, IPv6 routing, or application-level problems. Developing a methodical troubleshooting process helps identify and resolve issues efficiently. The first step in troubleshooting is always to verify basic IPv4 connectivity. Remember that ISATAP tunnels run over IPv4, so if the underlying IPv4 network has problems, ISATAP will not work. Test IPv4 connectivity between the ISATAP host and the ISATAP router using standard tools like ping or traceroute. Ensure that the host can reach the router's IPv4 address and that no firewalls are blocking communication. Next, verify that Protocol 41 traffic is permitted on the network. This is a common source of problems because many firewalls and routers filter Protocol 41 by default, or only permit standard protocols like TCP and UDP. You can test this by attempting to send Protocol 41 packets and verifying they reach their destination. On Linux, tools like HPING3 can craft Protocol 41 packets for testing. If Protocol 41 is blocked, ISATAP tunnels cannot be established regardless of other configuration. Once IPv4 and Protocol 41 connectivity is confirmed, check the ISATAP interface configuration on the host. Use commands like ipconfig on Windows or ipaddr-show on Linux to display the ISATAP interface and its assigned address. Verify that the interface is up and has an IPv6 address in the correct format with the 5EFE identifier. If the interface doesn't have an address or the address is incorrect, review the router advertisement configuration and ensure the host is receiving advertisements. Testing end-to-end IPv6 connectivity through the ISATAP tunnel requires IPv6-capable tools. The ping6 command tests ICMPv6 echo functionality through the tunnel. Try pinging the ISATAP router's IPv6 address first to verify tunnel connectivity. Then try pinging remote IPv6 destinations to verify routing and forwarding. Traceroute 6 or Tracert 6 on Windows shows the path that IPv6 packets take, helping identify where routing failures occur. Packet capture is invaluable for detailed troubleshooting. Tools like Wireshark or TCP dump can capture both the outer IPv4 packets and the inner IPv6 packets of ISATAP traffic. This allows you to see exactly what is being sent and received. Look for router advertisements to verify the prefix being advertised. Examine IPv6 messages for error conditions, and check that encapsulation and decapsulation are happening correctly. Capturing on both the host and router sides can reveal where packets are being dropped. ISATAP performance considerations. Performance is an important consideration when deploying ISATAP because the encapsulation overhead and routing through tunnels introduce latency and reduce throughput compared to native IPv6. Understanding these performance characteristics helps in capacity planning and setting realistic expectations for ISATAP-based networks. The most obvious performance impact is the additional processing required for encapsulation and decapsulation. Every packet must be wrapped in an IPv4 header when entering the tunnel and unwrapped when exiting. This happens in the network stack of the sending and receiving systems. Modern CPUs handle this efficiently, but it is not free. The overhead is particularly noticeable on high-throughput connections or systems with limited CPU resources. Servers handling many ISATAP connections may need additional CPU capacity compared to native IPv6. Packet size overhead affects bandwidth efficiency. Each IPv6 packet gains a 20-byte IPv4 header when encapsulated. For small packets like those used in interactive applications or voice over IP, this represents a significant percentage overhead. For example, a 60-byte IPv6 packet becomes an 80-byte IPv4 packet, adding over 33% to the packet size. For larger packets approaching the MTU, the percentage overhead is smaller but the absolute overhead accumulates across many packets. MTU mismatches can cause fragmentation issues that severely impact performance. If the ISATAP tunnel's effective MTU is not properly communicated to applications, large packets will be fragmented. Fragmentation requires additional processing and introduces opportunities for packet loss since all fragments must arrive for reassembly. Path MTU discovery for IPv6 over ISATAP is complex because it involves coordination between IPv6 MTU discovery and IPv4 MTU discovery on the underlying network. Routing inefficiency is another performance consideration. In native IPv6 networks, traffic can take the most direct path between source and destination. With ISATAP, all traffic must route through the ISATAP router, even if the source and destination are on the same logical network. This creates a traffic trombone effect where packets make an extra hop to the router and back. For local traffic, host-to-host tunneling can mitigate this, but it requires that both endpoints support ISATAP and can establish direct tunnels. ISATAP versus other transition mechanisms. ISATAP is one of several IPv6 transition mechanisms, and choosing the right mechanism for a particular scenario requires understanding how they compare. Each transition technology was designed for specific use cases and has different strengths and limitations. ISATAP is optimized for intra-site deployment, but other mechanisms may be more appropriate for different scenarios. 6-to-4 is another tunneling mechanism that is often compared to ISATAP. The key difference is that 6-to-4 is designed for site-to-site connectivity across the Internet, while ISATAP is for host-to-router or host-to-host connectivity within a site. 6-to-4 uses the special IPv6 prefix 2002::/16 and embeds public IPv4 addresses into IPv6 addresses. This allows automatic tunneling between sites without requiring pre-configured tunnel endpoints. However, 6-to-4 requires public IPv4 addresses and does not work well behind NAT, making it unsuitable for many enterprise scenarios where ISATAP excels. Teredo is a transition mechanism specifically designed to work through NAT devices. It uses UDP encapsulation rather than Protocol 41, allowing IPv6 packets to traverse NAT devices that understand UDP but not Protocol 41. Teredo also includes NAT traversal mechanisms similar to those used in VPN and peer-to-peer applications. While this makes Teredo more deployable in consumer environments, it introduces additional complexity and overhead. Teredo is typically used as a last resort when neither native IPv6 nor ISATAP is available. Tunnel brokers provide another approach to IPv6 connectivity. These are services, often provided by ISPs or third-party organizations, that offer configured tunnels to users. A user connects to a tunnel broker server which provides them with an IPv6 prefix and acts as their IPv6 gateway. This is more manually configured than ISATAP but works across the internet and doesn't require enterprise infrastructure. Tunnel brokers are popular for individuals wanting IPv6 connectivity when their ISP doesn't provide it natively. Dual Stack Lite, or DS Lite, is a newer mechanism designed for ISP networks. It assumes that the ISP network is primarily IPv6 with IPv4 provided through tunneling, which is the opposite of ISATAP's assumption. In DS Lite, customer equipment has native IPv6 and uses tunnels to reach IPv4 destinations. This represents the endgame of IPv6 transition where IPv6 is native and IPv4 is the legacy protocol requiring special handling. ISATAP represents the earlier transition phase where IPv4 is native and IPv6 requires tunneling. ISATAP deployment scenarios. Understanding practical deployment scenarios helps network architects determine when ISATAP is the right solution. Different network environments have different requirements and constraints, and ISATAP fits some scenarios better than others. Let's examine several common deployment patterns where ISATAP provides value. The enterprise campus network is perhaps the most common ISATAP deployment scenario. Consider a large corporation with multiple buildings on a campus, all connected via an existing IPv4 network infrastructure. The organization wants to begin deploying IPv6 capable applications and services but cannot afford to upgrade all network equipment immediately. ISATAP allows them to enable IPv6 connectivity for hosts that need it while leveraging the existing IPv4 infrastructure. The ISATAP router can be deployed at a central location, perhaps in the data center, providing IPv6 gateway services for all campus users. Remote office connectivity represents another strong use case. Imagine a company with headquarters and several branch offices connected via MPLS or VPN over the internet. The headquarters has native IPv6 connectivity, but the branch offices only have IPv4. Deploying ISATAP routers at each branch office allows employees there to access IPv6 resources at headquarters through the existing IPv4 WAN links. This avoids the cost and complexity of upgrading WAN infrastructure while still enabling IPv6 application deployment. Data center virtualization environments benefit from ISATAP in specific scenarios. In a data center with many virtual machines running on an IPv4 virtual network, ISATAP can provide IPv6 connectivity to those virtual machines without requiring the hypervisor or virtual switch infrastructure to support IPv6 natively. Each virtual machine can run an ISATAP client, and a virtual ISATAP router provides gateway services. This approach works particularly well during migration phases when some workloads need IPv6 but the underlying virtualization platform hasn't been upgraded yet. Testing and development environments frequently use ISATAP. Developers building IPv6 capable applications need IPv6 connectivity for testing, but the development network might be IPv4 only. Setting up a local ISATAP router provides developers with IPv6 access without requiring network team involvement to reconfigure production infrastructure. This allows rapid provisioning of test environments and experimentation with IPv6 features. The isolated nature of ISATAP also means that development IPv6 traffic is kept separate from any production IPv6 networks. ISATAP limitations and challenges. While ISATAP solves specific transition problems effectively, it has several limitations that network architects must understand. These limitations stem from the fundamental design of ISATAP and the constraints of tunneling IPv6 over IPv4. Recognizing these challenges helps in planning deployments and setting appropriate expectations. The requirement for Protocol 41 support is a significant limitation. Many network devices, particularly older firewalls and NAT gateways, do not handle Protocol 41 correctly. Some drop Protocol 41 packets entirely. Others allow them but do not include them in stateful inspection or logging, creating security blind spots. NAT devices are especially problematic because Protocol 41 does not have port numbers like TCP and UDP, making it difficult for NAT to multiplex connections from multiple internal hosts. Scalability concerns arise in large deployments. Each ISATAP host maintains tunnel state, and the ISATAP router must handle tunnels from potentially thousands of hosts. While modern routers have sufficient processing power for this, the router becomes a single point of failure and a potential bottleneck. All IPv6 traffic from ISATAP hosts must pass through the router, concentrating load. Unlike native IPv6 where traffic can be distributed across multiple routers, ISATAP creates a hub-and-spoke topology centered on the ISATAP router. Management complexity increases with ISATAP deployment. Network administrators must maintain two parallel addressing schemes and routing systems. IP version 4 and IP version 6 routing must be coordinated to ensure consistent behavior. Troubleshooting becomes more complex because problems could exist in the IP version 4 layer, the tunnel layer, or the IP version 6 layer. Monitoring systems need to track both protocols and understand the relationship between them. This operational overhead can be substantial, particularly during the learning curve period. Application compatibility issues occasionally surface with ISATAP. Some applications make assumptions about network topology or address format. These assumptions break when ISATAP is involved. For example, applications that perform address-based geolocation might malfunction because the ISATAP address does not map to a geographic location in the same way a native address would. Applications using IPv6 extension headers might have problems because some ISATAP implementations do not handle extension headers correctly when encapsulating packets. The temporary nature of ISATAP is both a limitation and a design feature. ISATAP was never intended as a permanent solution, but rather a transition mechanism used during the migration to native IPv6. This means that any investment in ISATAP infrastructure and expertise is inherently short-term. Organizations must eventually migrate to native dual-stack or IPv6-only networking. The effort spent deploying and managing ISATAP does not contribute to the end-state architecture, representing a sunk cost that provides no long-term value. ISATAP migration planning. Migrating away from ISATAP to native IPv6 requires careful planning to avoid service disruptions. Since ISATAP is a transitional technology, organizations should have a clear migration path from the beginning. Understanding the migration process and planning for it ensures that ISATAP serves its purpose without becoming a permanent fixture that hinders long-term network evolution. The first step in migration planning is establishing a timeline. This timeline should align with broader network modernization efforts and consider factors like hardware refresh cycles, application migration schedules, and staff training plans. A typical migration might span several years, with ISATAP serving as a bridge during the transition. The timeline should include milestones for enabling native IPv6 on network segments, migrating applications, and eventually decommissioning ISATAP infrastructure. Segmented migration is usually the most practical approach. Rather than attempting to migrate the entire network simultaneously, migration proceeds segment by segment or application by application. For example, you might start by enabling native dual stack on the data center network, allowing servers to communicate via IPv6 natively while still supporting ISATAP clients from other network segments. As additional segments are upgraded, they transition from ISATAP to native connectivity, gradually reducing the ISATAP footprint. Application migration requires coordination with development teams. Applications using IPv6 through ISATAP should be identified and assessed for native IPv6 compatibility. Some applications might need code changes to work optimally with native IPv6, particularly if they make assumptions about address format or tunnel characteristics. A phased approach where applications are tested with native IPv6 in staging environments before production migration reduces risk. Critical applications might be migrated last to ensure maximum stability. Monitoring during migration is essential. Both ISATAP and native IPv6 should be monitored simultaneously during the transition period. This allows verification that native IPv6 is performing correctly before ISATAP is removed. Metrics should include traffic volumes, latency, packet loss, and error rates for both mechanisms. Comparing these metrics helps identify if native IPv6 is performing as well as or better than ISATAP, providing confidence to proceed with migration. The final decommissioning phase should be executed carefully. Even after all systems are using native IPv6, ISATAP infrastructure should remain operational for a period to catch any missed dependencies or edge cases. A decommissioning plan might involve first stopping router advertisements to prevent new ISATAP tunnels from forming, and then monitoring for any remaining ISATAP traffic. Only after confirming that no systems are still dependent on ISATAP should the tunnel interfaces be removed and the ISATAP router be decommissioned. Documentation should be updated to reflect the removal of ISATAP from the network architecture. Conclusion and future of IPv6 transition. ISATAP has served an important role in the gradual transition from IPv4 to IPv6, providing organizations with a practical mechanism to enable IPv6 connectivity while using existing IPv4 infrastructure. As we have explored throughout this presentation, ISATAP offers specific advantages for intra-site IPv6 deployment, particularly in enterprise environments where infrastructure upgrades must be phased and carefully managed. The technology demonstrates the principle of working with legacy infrastructure rather than requiring wholesale replacement. By encapsulating IPv6 in IPv4, ISATAP extends the useful life of IPv4 networks while enabling IPv6 deployment. This pragmatic approach has allowed many organizations to begin their IPv6 journeys without waiting for complete network modernization. The automatic address configuration and tunnel establishment reduce the manual configuration burden, making ISATAP relatively easy to deploy in supported environments. However, ISATAP's role is inherently transitional. As native IPv6 deployment becomes more widespread, the need for tunneling mechanisms decreases. Modern network equipment increasingly supports dual-stack operation natively, eliminating the need for tunneling. Cloud providers and internet service providers now commonly offer native IPv6 connectivity. The trend is clearly toward native IPv6 with IPv4 as the secondary protocol, rather than IPv4 primary with IPv6 tunneled. Looking forward, organizations should view ISATAP as a temporary measure rather than a long-term solution. New deployments should strongly consider native dual-stack whenever possible, using ISATAP only where necessary for specific legacy segments. The skills and knowledge developed working with ISATAP remain valuable as they transfer to understanding other transition mechanisms and the broader IPv6 ecosystem. The troubleshooting techniques, security considerations, and deployment patterns discussed here apply to many network transition scenarios beyond ISATAP specifically. The ultimate success metric for ISATAP is that it becomes unnecessary. When an organization's entire network operates with native IPv6 and ISATAP can be decommissioned, the transition mechanism has fulfilled its purpose. As the networking industry continues moving toward IPv6 first and eventually IPv6 only architectures, technologies like ISATAP will fade into history, having served their critical role in bridging the gap between two eras of Internet protocol architecture. Thank you for your attendance. Please consider subscribing to the channel.